Hello and thank you for watching. This project was created for the Honors Program at Wake Technical Community College in the fall of 2024, shining a light on 3D rendering, the fast inverse square root, and Newton's method in action. Accurately calculating the direction and intensity of light in 3D rendered environments creates more realistic surroundings and immersive gaming experiences. Games use vector normalization to calculate the direction of lighting off a surface. This involves changing coordinate lengths of a vector to 1 without changing its direction. The formula for this involves dividing the vector by its magnitude, requiring an inverse square root. This can be taxing on a system calculating thousands of surfaces in 3D builds, especially in early gaming, when memory overhead was inhibited by hardware constraints. The fast inverse square root algorithm is a response to those constraints. It provided accurate, real-time solutions while also providing more responsive and visually smooth experience in rendered environments. It calculates the inverse square root of a number with minimal memory overhead because the algorithm requires fewer operations than rudimentary techniques. The reduction in memory usage was important in earlier days of computing when hardware constraints on software were much tighter. As a basic example, imagine a light source and a cube. The light source emits many rays of light that bounce off the cube's surfaces at different angles. To calculate the direction of each ray of light, the coordinate lengths are normalized to 1 unit, and 1 over the square root of x squared plus y squared plus z squared is calculated. This project focuses on this calculation, and how the inverse square root of some number can be calculated quickly and accurately in a program. The fast inverse square root algorithm efficiently calculates the inverse of the square root of some number. It is known for its use in the code for the game Quake III Arena, as it was 4 times more efficient at finding an accurate solution than other methods of the time, with less than a 1% margin of error. The algorithm implements Newton's method and bit hacking on numbers represented by the IEEE 754 format for floating point numbers. This means that raw bits are manipulated in the program instead of numeric representations of decimal numbers, providing a more accurate calculation. Before applying Newton's method, the algorithm approximates a first best guess solution using bit-level manipulation. Floating point numbers, or decimal numbers, are interpreted as bits and are adjusted directly, providing a more accurate first best guess. A magic constant is applied to the bits of a floating point number, greatly reducing the iterations needed in the next step. Newton's method takes the best guess provided by the bit hacking step and iteratively approximates the solution for the fast inverse square root. Because of the bit manipulation step, it only takes 1 iteration to provide a highly accurate approximation. These methods are less computationally expensive than using Newton's method alone, making the algorithm indispensable in an era of limited computing power. This is the original code used in Quake III Arena. Line 1 states that the rest of the code is within a method that takes a float, called number, as a parameter. Lines 2, 3, and 4 declare essential variables for the method. The variable I is declared as a long and will be used for bit-level manipulation of a floating point number. The variables x2 and y are declared as floats, where x2 will store half of the input number and where y will store the input number and intermittent results throughout the method. The variable 3/2 is declared as a constant float, therefore it will not change throughout the method. Lines 6 through 14 execute the logic of the fast inverse square root, where line 6 calculates half of the value of the method parameter, number, and assigns it to x2, while line 7 assigns y the value of number unaltered. Line 8 reinterprets the bits of y as a long integer without changing the binary representation. This is a trick using the IEEE 754 representation of a float decimal. Line 9 uses the magic number on the result of the bit hacking. The original creators noted the unique application in their own colorful comment to the right. Line 10 converts the manipulated bits back to a floating point decimal, and line 11 performs 1 iteration of Newton's method. Line 12 is a second iteration of Newton's method, though this is commented out and unused in-game. This table shows the accuracy of the fast inverse square root program used in Quake III Arena. True values from the dataset show that estimates from the game are well within 1% margin of error, with a maximum margin of 0.375%. Newton's method is a root-finding algorithm often taught in Calculus 1. In the fast inverse square root algorithm, it is used to refine the approximated solution provided through the bit hacking step. It is represented mathematically as x sub 1 equals x sub 0 minus a function at x sub 1 divided by the derivative of the function at x sub 0. In this iterative calculation, the derivative of the function at x sub 1 cannot equal 0 and is the slope of the function at x sub 0. X sub 0 is the best initial guess provided by the bit hacking step. X sub 1 is the next approximation, and the function at x sub 1 is the function value at x sub 1. In the gameplay of Quake III Arena, the fast inverse light falloff can be seen in light fixtures and in some ammunition and weapons. In the first clip, the players emit light when firing a weapon that interacts with the environment and quickly fades in a short distance from the player. In the second clip, the emitted light is more visible with long-distance ammunition. As a contrasting example, Doom, released in 1993, uses light flashes that affect more than fast inverse light falloff lighting, and filters that cover the entire screen as a response to taking damage. The foundations of the fast inverse square root algorithm was first conceptualized by William Kahan et al. In an unpublished paper written at UC Berkeley in the late 1980s. It was later refined by Greg Walsh et al. At Ardent Technologies, where the magic constant was developed for a more accurate solution. The final algorithm was developed using this groundwork and implemented by John Carmack in the 1999 game Quake III Arena. The method was faster and more efficient than others of its time, such as table searching, and more immersive than simplistic solutions such as manipulating a 3D object's mesh. Similar methods were also applied in game development and 3D development environments during and since the fast inverse square root's development. These include Crystal Space Game Development Kit in 1997, the Titan Game Engine in 2004, and Fastcode open source library of optimized routines in 2003. Today, the improvement of graphic processing units has rendered the fast inverse square root obsolete, though it is still a lighting option available for use in 3D development programs such as Blender or Maya. The fast inverse square root serves as an example of how calculus affects computational methods. It showcases how mathematical concepts like derivatives and approximations are used to solve real-world problems efficiently. Due to developments in this algorithm and similar concepts, gaming and 3D development became more efficient and immersive. It paved the way for historically innovative solutions in technology and highlighted the importance of collaboration and research.